let me show you two shapes. I claim that these shapes are different. I know it's hard to tell, the difference is extremely subtle, but the cool thing about math is that it lets us develop tools to detect differences in shapes like this. And a lot of the math involved in multivariable integral calculus is developed with this goal in mind. And it may seem like a tall order, but I claim by the end of this video you will have the tools to tell me the difference between these two shapes. This is the power of math, developing tools and building theories to tackle a question that a 3-year-old could answer. Math is beautiful, isn't it? Now, in order to hone our abilities as glorified hole finders, I want to start this video by giving a quick summary of some of the new language and fun facts that are involved in this topic. We're dealing with operations on vector fields, so I want to draw the picture that I have in my mind when I'm thinking about all of this. I'll draw the 3-dimensional case, but there are analogous pictures in all dimensions. We've learned about a number of operations, in particular the gradient, the curl, and the divergence. We want to think about the gradient as something which eats a function and spits out a vector field. We want to think about the curl as something which eats a vector field and spits out another vector field. And finally, the divergence is something that eats a vector field and spits out a function. The most important definition for today is that a vector field is conservative on some domain D if you can find a scalar function little f on that domain such that when you take the gradient of f, you get the vector field f. If you can do this, we call little f a potential function. So in my picture, I'm thinking about the vector field f as living here, and I'm searching for a little f over here, which gets sent to that function under the gradient map. Loosely, you can think about little f as being an antiderivative of sorts to capital F. It's something that when you take the derivative, you get capital F. Conservative vector fields are great for a number of reasons, but the main fun fact we have is the following. This is called the fundamental theorem of conservative vector fields. It's sometimes also called the fundamental theorem of line integrals, and you should think about this as being a generalization of the fundamental theorem of calculus. So here's what it says. If we have a conservative vector field capital F with potential function little f, and C is some oriented curve from a point P to a point Q, then to evaluate the vector line integral of f along this curve, you just plug in the points Q and P into the potential function and subtract. In a minute, I'll give you some intuition as to what this is saying, but first I want to write down a couple immediate consequences. These next two facts aren't saying anything new or different. I really think about them as just different ways to interpret this theorem that I just wrote down. For example, suppose that we have a conservative function, and I have two different curves from the same point P to the same point Q. Well, by the above theorem, the line integrals of the vector field over these two curves are both equal to little f of q minus little f of p. In other words, they're the same. To rephrase what I just said, if you have a starting point P and a finishing point Q, in a conservative vector field, it doesn't matter how you travel from P to Q, the vector line integral will be the same. This first consequence is called path independence of conservative vector fields. Again, it's just a different way to interpret the theorem. Similarly, what if we have a conservative vector field and C is a closed loop, so like a circle or something like that? What does this theorem tell us about the line integral of the vector field along C? Well, in a closed loop, the starting and finishing points are the same. So by the theorem, the line integral would be f of p minus f of p, which is 0. So this tells us over any closed loop, a conservative vector field is going to be 0. We'll get some practice using these facts soon, but I want to give you some intuition for what this main theorem is saying. This idea that I'm about to describe I think is really cool, and it really ties together a lot of these concepts. So I'm going to describe this when the domain is R2, but the idea generalizes to any dimension. So suppose we have a conservative vector field on R2. Again, what does this mean? This means that the gradient of the potential function is our vector field. I want to give you an interpretation for what the vector line integral is measuring. To do that, I'm going to draw a couple pictures. I'll start out by drawing the domain. Here's the two-dimensional world, and let me just sketch a random vector field. For example, we could consider this radial-looking vector field that is 0 at the origin and points outwards. To help understand what's going on, I want to remind you of a couple facts about the gradient from when you first learned about it. One of those facts is that the gradient of little f is pointing in the direction that little f is changing a lot. In other words, if you're in the domain and you follow the vector field, you will be traveling up the graph of the function. A related fact is that if we were to draw level curves of our potential function, this vector field, which is the gradient of that function, would be perpendicular to those level curves. So for example, I could sketch a couple level curves in purple and they would probably look something like this. And to remind you what these curves mean, they're curves of constant function values. So if you thought about this as a contour plot of a mountain range, if you walked along these purple circles, your height would be constant. And if you followed the green vector field, your height will increase. So let me try to draw what's going on in 3 dimensions. Remember, our vector field is a vector field on R2. So I'll draw the xy plane with the z-axis. The green vector field just lives in the xy plane. It would look something like this. And then based on what we know about the level curves of this potential function, the graph of this potential function probably looks something like this. And you can see the purple level curves as being circles of constant height. Okay, so now that we have some pictures, we want to think about a vector line integral along a curve in the domain. For example, here's a random curve. In the 3-dimensional picture, that curve itself, again, this just lives in the xy plane. It would look something like this. But what you want to be thinking about is the corresponding path on the mountain range upstairs. So if the blue and purple surface represents a mountain range, you can think about this curve as describing a hike that we're taking, starting at this point and finishing at this point. And the path in the domain lifts to some path along this mountain range. The quantity that we're interested in is the vector line integral of the gradient vector field. Well, very roughly, what does the gradient represent? It represents a small change in f. And what do we do when we integrate? We add things up. So a line integral like this is adding up a bunch of changes of the function. And when we do that, we get the net change in elevation. In other words, this line integral returns the net change in height when you walk along this path. And here's the point. If you're hiking along this mountain range, it doesn't matter what path you take. The net change in elevation is just determined by where you start and where you finish. You could walk along a crazy path like this, but your starting and finishing heights are the same. This is all the fundamental theorem is saying. Now, the point of all of this is that the fundamental theorem only holds for conservative vector fields. So this visual analysis of thinking about the graph of a potential function should not work for a non-conservative vector field. So before we do some examples, I want to give you one last piece of visual intuition. This one is really going to test my drawing skills, so be patient. But what I want to do is play the same game with a non-conservative vector field and see what goes wrong. We'll think about this in 2 dimensions again. So I'll draw another random vector field, but this time it'll be a swirly vector field like this. Let's say it's undefined at the origin, and then it swoops around like this so that the flow lines are circles. Now before we move on, I just want to make a clarification. I started it out by saying that we'll be discussing a non-conservative vector field, but whether or not something is conservative depends on the domain. And the whole point of this visualization is that this vector field could be conservative depending on which domain we pick. So again, we want to think about this green vector field as representing the gradient of some function. If that were the case, then these vectors would be pointing in the direction of increase of the function. And like I talked about a couple minutes ago, the level curves of a hypothetical potential function would be perpendicular to the vectors. So if such a function existed, the level curves would look something like this. Okay, so let's try to find a potential function. The first domain I want to consider is the left half plane. So by that I mean the set of all points where the x value is negative. In the domain picture, that would look something like this. And then below, I'm going to do the same thing that I did before and think about the 3-dimensional world to draw a graph of a potential function. The vector field is living in the xy plane, and the domain that I just described would look something like this. Now, if this vector field is the gradient of something, we would need to find a function which is increasing along the green vectors. Again, I'm no artist, but you would get some kind of spiral staircase shape like this. Now, the origin is not part of my domain. You can't really tell from my picture, but I'm just defining this staircase over the yellow region. And you can imagine that this staircase just extends infinitely across the yellow region. And it seems like we've found the graph of a potential function that plays nicely with this vector field. So obviously this is imprecise, but this is a visual argument that would indicate that over this domain, the vector field is conservative. Well, let's keep going. Let's try a slightly bigger domain. Let's consider the domain which is everything except the first quadrant. On the domain picture, that would look something like this. Again, if we want to find a potential function, we want to find a graph which is increasing along the vector field. We could draw the same kind of spiral staircase structure, which maybe starts at 0 along the positive y-axis, and then as we circle around the vector field, the spiral staircase goes up and up and up. And again, you can imagine this staircase extending infinitely along the yellow region. And again, it seems like we've found the graph of a function whose gradient looks like our vector field. So, on this domain, the vector field is conservative. But now I want to consider the domain, which is the entire plane except for the origin. If we tried to build our potential function as before, now we run into an issue. The spiral staircase starts at 0 along the positive y-axis, and then the function needs to increase along the green vectors. So I circle around in the domain and I go up the spiral staircase. But what happens when we get back to the positive y-axis? Well, by the nature of a spiral staircase, we're directly above where we started. This has to happen. And what's the problem? This can't be the graph of a function. One of the first things you learn as a baby is that a function has to satisfy the vertical line test. So if you think about continuing to walk in circles in the domain, that would mean you're going up, 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 up forever and ever and ever on this spiral staircase. And by the nature of a spiral staircase, it is for sure going to fail the vertical line test. It's impossible to describe a shape like this, which is the graph of some function. So what we've found is that on this domain, the vector field is not conservative. No such potential function exists precisely because we can walk in a closed loop like this to go up the spiral staircase and end up at an elevation directly above where we started. Anyway, hopefully this gives some indication as to what the fundamental theorem is saying and why it might be true. This is at least the kind of picture that I have in my head when I'm thinking about this stuff. Now that you've put up with my visual poetry for a while, we can do some examples. We'll start off with something relatively straightforward. In this first example, I have a curve, and instead of describing the curve precisely, I'm just giving us a picture. It's this green curve that travels from the point 1, 1 to the point 3, 4. We also have a vector field f, and the goal of the problem is to compute the vector line integral of this vector field along the curve. Now, to bring up something I talk about a lot, right now you are watching a video all about the fundamental theorem of conservative vector fields. Unless you skipped ahead or paid no attention to what I was talking about for the first 10 minutes of the video, you have a lot of contextual information about what you should be doing. But if we were cornered in a dark alley in real life with this problem, we would not have that contextual information. So it's a healthy exercise to go through the motions of determining a good strategy for the problem. Now, what stands out to me here is that we are not explicitly told what this curve is. We're just given a subpar picture. So if I think about the usual way that I tackle line integral, how do I do that? Well, I parameterize the curve and then I just evaluate it. But I can't do that here. I don't know what the curve is. So I know that we're going to have to do something that does not involve parameterizing the curve. The only thing we know about the curve is the endpoints. So I open up my toolkit, and my newest shiny tool is the fundamental theorem for conservative vector fields. I know that if this vector field was conservative, I wouldn't have to worry about the path that I take, and I only care about the endpoint values. So let's cross our fingers, hope that this is conservative, and try to find a potential function. So what do we want to do? We want to find a function little f such that the gradient of that function is our vector field. And then when you set this up, what do you get? Well, the gradient of little f is the vector f sub x, f sub y. So that tells us that we would need the x derivative of f to be 3x squared plus 2y, and we would need the y derivative of f to be 2x. So this might be something that you can just eyeball, and if so, that's fine. As long as you demonstrate that your potential function is truly a potential function, I think you're okay. But this process can get complicated, so to describe a methodical way to go about doing this, we could start by partially integrating. We know that the potential function would have to look like the integral of the x derivative with respect to x. Well, that would be the integral of 3x squared plus 2y with respect to x, which would be x cubed plus 2xy plus a constant, which, with respect to x, this constant could be some function of y, and we don't know what that is. But we could figure it out using the y derivative. So we know that f has to look like this in pink. On the one hand, the y derivative we know has to be 2x. That came from our condition above. But then on the other hand, we could just take the y derivative of that pink expression. What would we get? Well, we would get 2x plus the derivative of this k function. So now we have a new equation, 2x equals 2x plus k prime of y, which means we just need to find a function k such that k prime is 0. Now, there's a lot of such functions. Any constant would work, but we may as well pick k to be 0. In a problem like this, you don't need to find the most general potential function. We just need to find a potential function. And so there we go. A potential function f is x cubed plus 2xy. What we've shown is that our vector field is the gradient of that function. An important point to point out is that the domain of both the vector field and the function we can take to be all of R2. The important point is that this curve lives entirely in this domain that I picked. And thus, by the fundamental theorem of conservative vector fields, the line integral that we care about is going to be the value of the potential function at the endpoint minus the potential function at the starting point, which is this. And then I tried to simplify this in my head and I got 49. And there we go. This is a basic example of using the fundamental theorem to evaluate a line integral. Next, we have an example that looks a little more scary. I'm giving us a curve, and I'm actually giving us a parameterization of the curve, cosine t sine t, t squared, for t between 0 and 2 pi. I'm also giving us a vector field which looks crazy, too crazy for me to read out loud. And as before, what we want to do is evaluate the vector line integral of this vector field along the curve. And I'm giving us a hint. I'm going to tell us that this vector field is conservative on some domain. Justifying that in this case would take a little bit of work, so I'm just going to tell us straight up it's conservative and we can use that fact. Okay, so what's the point of the question? Again, if you strip context from your mind, we have a line integral to evaluate, and we already have the parameterization of the curve that we care about. So the naive thing to do is to say, well, we can just evaluate the integral. Compute r prime, plug in the parameterization into the vector field, blah, 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 set up the single variable integral and just do it. And in theory, you could try, but I can already see that I really don't want to do that. The vector field looks insane, and you can think about plugging the parameterization into the vector field and then dotting with the derivative of that parameterization. You're going to get some crazy expressions. For example, just looking at the first component, you'd get something like a t squared e to the sine of cosine of t times cosine of t. I like integrals, but that doesn't sound very fun to integrate. So the point is that we probably don't want to evaluate this line integral exactly as written. So instead, we'll think of something clever to do to simplify the problem. And the hint we were given is that f is conservative. What do we know about conservative vector fields? They're path independent. In other words, the journey doesn't matter, only the starting and end points matter. Now, one approach you could take here is you could try to mimic what we did in the previous problem. We could figure out the starting and end points of this curve, and then we could just find a potential function, and then plug in the points and we'd be done. But I also don't really want to do that, because looking at the vector field, again, it's crazy. So instead of doing that, I'm going to use path independence to integrate along a different curve. Maybe we can find a simpler, more direct path which drastically simplifies the integral. And indeed, if we think about the curve in the domain, so the domain is three-dimensional here. This is a three-dimensional vector field. The domain that we're given is for positive z values and for non-zero x and y values. So that means we don't include the z-axis, and we get something like this. And what does this curve look like? Well, the x and y values are given by cosine of t and sine of t. So in the xy plane, we're just going around in a circle. The z coordinate is t squared, which means as time increases, the z value is going up. So this is some kind of helix shape. At time 0, we start at the point 1, 0, 0. And then at the end of our parameter domain, which is 2 pi, we're at the point 1, 0, quantity 2 pi squared. So we've done one full rotation and we're above our original starting point. Like I mentioned, the goal here is to find a simpler curve to integrate over. And it looks like we could take the straight line from our starting point to the finishing point. Seems like it'd be a lot simpler than this helix thing. So let's call that curve C2. It's a line segment. We're pros at parameterizing line segments, so I'll do this quickly. We have our starting point, which is 1, 0, 0. We have a direction vector, which is our finishing point minus our starting point. That would give me the vector 0, 0, 4 pi squared. Then a parameterization of that segment would be the starting point plus t times our direction vector, and we could send t from 0 to 1. The point is that this curve is in our domain, and it has the same starting and ending points as our original curve. So because we're told that the vector field is conservative by path independence of conservative vector fields, the line integral that we care about is the same as the line integral over our new curve. And the point is that this is going to be much easier to evaluate. We can evaluate it as usual. We turn it into a single variable integral from 0 to 1 coming from our new parameter domains. We'll get f of our parameterization dot r prime of t. Now look at r prime of t. It's going to be the vector 0, 0, 4 pi squared. So I'm being a little lazy here, and I encourage you to work out the details to make sure you understand what's going on. But we're going to take the dot product of something with the vector 0, 0, 4 pi squared. The only thing that will survive that dot product is the z-coordinate of the vector field vector. So in the end, we'll get 4 pi squared times the z-coordinate of the vector field. But when we plug the parameterization into this vector field component, y is 0, so this whole term goes away. X is 1, so the z component of the vector field along this curve is just e to the sine of 1. So the integrand in our new integral is the constant 4 pi squared times e to the sine of 1. And integrating that from 0 to 1 gives you 4 pi squared e to the sine of 1. Again, that last step was a little fast, but I'm just evaluating the line integral over this new red curve as usual. But with that, we're done. We have this crazy vector field and this crazy curve, and we were able to use the fact that the vector field is conservative to quickly evaluate the line integral that we care about.